So welcome. There's going to be 4 chapters on heat and thermodynamics. I'm going to start off with this first chapter, which is on basic definitions. When I was a student, I tended to blow off the definitions because I saw it all as a problem-based course, but then I'd pay the price because I didn't know what the questions were really talking about. So pay attention to what the terms mean. There is a bit of historical issue here in that this was one of the last bits of what we call the canon of physics to be resolved. Much later than most people think. 150 years ago, they were still scratching their head, kind of talking about what energy was. Well, maybe 160 years ago, but so it wasn't. Newton didn't sort this out. It came much later than Newton. You're looking at something that you can't easily see, and you're trying to visualize what's going on in a consistent way. So it's not easy. So you recognize things. You get your theories, which are repeated observations of what's going on with explanation. And then after a while, you get to bedrock, and you call that your laws, and you have a few laws. And when you get to the stage where you realize that something was missed out, that's more fundamental, you want to make it a law, but you don't know what to call it. You don't want to call it the third law when it's the first thing that people should know. But you've already called something else the first law. So you call it the zeroth law. So we have this thing called the zeroth law, which is basically, my interpretation anyway, is that they said, oh, we should have really emphasized this. And that just puts people off immediately. Man, zeroth, what's a zeroth law? This is like wacky. So we're going to talk about temperature in the zeroth law. We're going to talk about thermometers and temperature scales, a thermal expansion, and then we'll talk about macroscopic. That means the big view of ideal gases. Sometimes in this we talk about solids, sometimes we talk about liquids, sometimes we talk about gases. It depends upon what shows the effect we want to talk about most clearly. So temperature in the zeroth law. Temperature is a direct measure of the average molecular kinetic energy. We didn't know that for the longest time. You knew hot and cold. You could even measure hot and cold using a thermometer. But you needn't really understand what this is about. They thought there was this caloric fluid which basically made things hot. And if you put more of the caloric fluid in, it was hotter. If you put less of the caloric fluid in, it was cooler. When you made something hot, you poured caloric fluid in. So hot things lost caloric fluid and made things that didn't have much caloric fluid warmer. Total nonsense. It's like, But it, on a simple level, it works. It's just eventually the evidence comes that, no, this doesn't explain enough. We've got a better model. What do we know now? With hindsight, we know that there are such things as molecules and atoms. And we know that the more something, say in a solid, the more the atoms and molecules vibrate, then the higher temperature it displays. The faster the gas molecules are going, the higher the temperature it displays. So now we have a keen insight into what temperature is, but we didn't used to have it. And we're left with the tradition of the measurement systems for temperature from before we knew what we were doing. So we have temperature scales that are not based upon average kinetic energy per particle. They're based upon anything that changes with temperature. So how does that column of alcohol expand? How does that column of mercury expand? How does the volume of this gas expand? How does the resistance of this thermometer change? How does the color of a little liquid crystal change with temperature? Anything that changes with temperature we'll use as a thermometer, because initially we didn't know what the heck was going on. So temperature is the direct measure of the average molecular kinetic energy, but we didn't always know that. 2 objects are in thermal equilibrium if no heat energy is exchanged between them, despite the fact that they are in thermal contact. What it means is the two objects have the same temperature. When you have, so if temperature measures the average kinetic energy per particle, when you have the same temperature, you have the same average kinetic energy per particle. And if I have the same temperature as you, you have the same temperature as me, I have the same kinetic energy per particle as you, you have the same kinetic energy per particle as me. Two objects are in thermal contact with each other when heat energy can be exchanged between them. There's no insulator between us. We're touching, heat can be exchanged. And heat is the transfer of energy from one object to another object as a result of the difference in temperature between the two. It's almost like we're going in a circle here, and we are to some extent. We call heat, we reserve heat for the name for energy that's in transition between one object and another that's caused by a temperature change. It's like salary. Salary is just money. But we consider the payment of salary and the receipt of salary so important that we give it its own name. We call it salary, so it won't be confused with other amounts of money. And heat is so important we give it its own name. It's energy, just like thermal energy inside the block, just like other forms of energy. But when it's been transferred from one object to another because of a temperature change, we call it heat, because we want to be very specific about it. So you can't get the transfer of heat if there's no thermal contact, because the insulator is going to stop the heat from flowing. So thermal contact is we're touching in such a way that heat could flow, and heat is what would flow if there's a temperature change. If there's no temperature change, then no heat will flow, and we say these two objects are in thermal equilibrium. So new terminology there, and they're going to talk in terms of that terminology, so it's good to be able to talk thermal. You've got to be able to, not just know what thermal equilibrium means, but be able to use it in a sentence kind of thing, The zeroth law states, this was the law they went back and gave us, states that two objects have the same temperature if they're in thermal equilibrium. That's the, if you like, that's the Bonaquisti version. If you look in the textbook, it'll talk about objects being in thermal equilibrium and all that kind of stuff. But in the end, it means, it'll talk about three objects, A, B, and C. If I'm in thermal equilibrium with A, and I'm in thermal equilibrium with B, then A then A and B are in thermal equilibrium with each other. But what it really means is, if I have the same temperature as you, and you have the same temperature as him, I have the same temperature as him, because it's the same amount. It's simple as that. It's the zeroth law. Why did they even bother writing something so simple? Because this stuff gets confusing and people miss the obvious because they're not familiar with the terminology. So we have to write a law about it. Okay. Thermometers will use anything that will change, hopefully linearly, but even if it's not quite linearly, consistently with temperature change, anything. A thermometer indicates temperature by displaying some physical property that varies with temperature. Typical physical properties include, well, if volume changes, we'll use it. If the length of the thing changes, we'll use it. If the pressure inside the thing changes, we'll use it. If the resistivity changes, we'll use it. If the color changes, we'll use it. We'll use whatever we can. Okay, so we get a change. We need to put numbers on this change. How do we do it? Well, Fahrenheit did it. And then about 45 years, I used to have the dates on this, which was kind of interesting. I took the dates off to make it a bit more streamlined, but Celsius did it about 45 years later. So, and they were both, basically a couple hundred years ago. Fahrenheit is the scale that's used in America for day-to-day temperatures, but not very many other places in the world use Fahrenheit. If you watch international TV, then you get the weather in terms of degrees Celsius. I tend to watch Sky News because it comes with Apple TV. And it has a world globe and it shows the temperature around the world. And And just, you know, the highest temperature I've seen to date is 45 degrees C. That's hot. That's like, you know, 49 degrees C. 49 degrees C. I've never seen a 50. I want to know what colour scheme they're going to use for 50 degrees C. Seen 49. That was in Kuwait City, Kuwait. They don't have all the bits, not every bit of the world, it's just the cities that they look at, major cities. So rest of the world uses degrees Celsius throughout. We use Fahrenheit for colloquial things and degrees Celsius in the science lab. Fahrenheit must have been some kind of idiot, because the boiling point of water is 212 degrees Fahrenheit and the freezing point is 32 degrees Fahrenheit. And, you know, what a disaster. Well, not so much, actually. What he did was, he was interested in biology, from what I gather, and he wanted to make human body temperature about 100 degrees Fahrenheit. And he picked brine, which is basically salted water, to get as cold as he could get. And he got down to basically minus 32 degrees. Well, it got down to a cold temperature, which was 0 degrees, which was 32 degrees below what water freezes at. And he called that 0 Fahrenheit. So there's a lot of logic, although for conversions we need to know the 212 and the 32. 45 years later or so, along comes Celsius. Celsius is, you know, dealing with hundreds, makes the boiling point of water, called the steam point of water, 100 degrees Celsius, makes the ice point of water 0 degrees. This is ice, water melting from ice. As the water immediately melts from the ice, what does its temperature have? 0 degrees. The ice can be colder, of course, yeah? And the steam, as soon as the steam is produced, what temperature does it have? Not, you know. So if you get picky, they're very picky definitions, but, you know, boiling point, freezing point. Problem is completely nonsensical units, because 0 degrees F is not no temperature. 0 degrees C is not no temperature. We can get negative temperatures. How can you get negative temperatures? Temperature is the average kinetic energy per particle. How can you get negative average kinetic energies? It's a number scale. We don't know where no kinetic energy per particle is. We don't know where the coldest point in the universe is. So rather than trying to find that 0, we basically say, we'll just take ice as being 0 degrees C, and we'll take boiling water as being 100 degrees C, and if you're colder than that, you'll have a negative number. For addition and subtraction, who cares? You want to add 10 degrees? You add 10 degrees. You go from minus 90 to minus 80. You go from plus 10 to plus 20. You added 10 degrees. Who cares? For multiplication and division, it's a disaster. Because if I double 10 degrees to 20 degrees Celsius, I don't have twice of anything apart from the number on my answer. I've not got twice the amount of kinetic energy per particle. I've not got twice. It's a bit like, will you do me a favour? Will you come out with me? You just come and stand next to me. This is a bit, we're almost at the end of class. We can, okay. So we live in a swamp, so you never see our feet. So all you can see is us above the water. So you say, how much taller is he than I? And you go, twice as big, I think, yeah? Twice as big. This is how tall I am. He's that tall. Twice as big. Fair enough? Because we don't know how deep the swamp is. The swamp might be an inch deep, in which case it's still twice as big as me. Or the swamp might be a mile deep, in which case it's very little taller than me. But when we go and stand at the side, you can see that, well, actually I'm not going to cheat now. If you stand at the side, you can see that actually I'm probably even sat down, I'm 3/4 his height. I'm not half his height. Yeah. So by being able to see the beginning means that the ratio is really correct. Thank you. The ratio is really correct. You can't do a ratio when you don't know where zero is. Okay? So you've got to know where zero is. And actually, Lord Kelvin, William Thomson, basically in about 1880, kind of realized we have no idea where absolute zero is, and we need to find it, because until we find it, we can't make progress. And so he argued for the absolute temperature scale, which we now call the Kelvin scale after him. And basically, the absolute zero is no kinetic energy per particle. None. It cannot get colder than that. You can't have less kinetic energy than none. So it's none. So there is a coldest place in the universe, and we can actually get quite close to it. Hot, you can always add more energy, so in theory you can go on millions of degrees, and I suppose even higher, but you can't get colder than absolute zero. And once you find it, and once you use a temperature scale which starts at zero, has been zero kinetic energy per particle, now you can do ratios. Now you can double the temperature, and you doubled the kinetic energy per particle. You can triple the temperature, and you triple the kinetic energy per particle. Now it all makes sense. And so that's the Kelvin scale. And we're going to do a lab today where we're going to find the temperature in degrees Celsius of absolute zero. And it turns out that it's 273 Kelvin. So 0K is minus 273 degrees C, and 0 degrees C is plus 273 degrees Kelvin, because the size of the Kelvin and the size of the degree C are deliberately made to be the same size. So we're just changing our zero reference. For doing conversions, you can convert between degrees Fahrenheit and degrees C by using this conversion. And if you want to go from Kelvin to degrees C, you can use that conversion. I'm going to skip those. Actually, I'm going to just stop. I'm going to just do this. So convert 1400 degrees C into degrees K. We say K is equal to degrees C plus 273. So K is equal to 1400 plus 273, which equals 1673K. By tradition, we don't say degrees Kelvin, we say Kelvin. If I want to talk about a degree of Kelvin, I can say that's a degree of Kelvin, but we don't say 63 degrees Kelvin. We say 63 Kelvin. I tend to use both from time to time. Occasionally you'll run into somebody who's real picky about it, and they'll, it's kind of like people like to put people down sometimes. Again, this is why reading the book and reading around the subjects is important, so you speak the language, Degrees C into degrees F, I don't remember that quite well. I do remember the equation, actually. Degree F equals 9 over 5 degrees C plus 32. Whoa, 32. So degree F is equal to 9 over 5 times 66 plus 32. Degree F is equal to, did I bring my calculator? I don't believe it. I didn't bring my calculator. It's going to be, let's look, just double it. So that's 120, 132, about 160 something. I think it's going to be the 150. Am I right? Yeah, that's right. Yeah, okay. And then what is smaller unit? Oh, which is the smaller unit? So think of going from freezing point to boiling point. So this is ice, and this is water. And this is 32, and that's 212. And this is 0, and that's 100. And this is 273, and that's 373. So which is more divisions? Fahrenheit. Fahrenheit is the finer, not meaning better, but the smaller unit. Next time, we're going to do about thermal expansion. We're going to do about model constant gas model, P1 V1 over T1 equals P2 V2 over T2. We'll do about the mole, and we'll do about the molecular whatever next time.